column vector with that other vector. But this is not an ordinary dot product, it's a dot product, a scalar product with that symplectic structure, with that omega put in between. So it's like the replacement of a dot product, but with this guy here. See? And instead of a Kronecker delta, you have this. So this is increasingly becoming like it's playing the role of some kind of metric. So this is the symplectic dot product. And now you see the significance of two fellows whose Poisson bracket is 0. Namely, they are in involution with each other. It means that this dot product is 0. In a sense, these guys are the gradients are orthogonal to each other, but with this twisted sense. So the Hamilton formalism becomes much easier to write in this language here. And you'll see, next time you will see how this is going to play a role here. I have still to talk about what's meant by the integrability of a Hamiltonian system, and what's the idea of having these n fellows in involution, etc. But that will become easy to understand in this language. Geometrically, it will become intuitively very clear as to why this is playing a role at all. But the introduction of this matrix is going to make life extremely simple, as you can see. By the way, one last point, I may say so. We can ask, what does a canonical transformation do to this whole thing? Remember, a canonical transformation preserves this in here. And you can write this Poisson bracket in this language out here. So what does it imply? If from x, from QP, I go to QP, I call this guy x, I call this guy xi, to n-dimensional vector here, then the Poisson bracket relation implies, the canonical transformation implies, CT implies xi I, xi j equal to. That's what is meant by preserving the Poisson bracket. But the Poisson bracket can be written in this form. Okay. So what's it saying? It's saying that for a canonical transformation, x to xi is a CT if and only if. Plug it in here and equate both sides. This, and what do you get? The Jacobian matrix delta xi over delta x transpose omega delta xi over delta x must be equal to omega itself. So it says, whatever be the change of variable, we are assuming it's a smooth change of variable, etc. This Jacobian matrix at every point transposed with this omega, this guy here must be equal to omega. So then and only then is x to xi a canonical transformation. Now, of course, these are 2n dimensional matrices, 2n by 2n matrices. Any matrix which satisfies, any 2n by 2n matrix which satisfies mt omega m equal omega implies m is a symplectic matrix. It's called. The next step is to show that symplectic matrices form a group, which means that if you make two subsequent canonical transformations, it's equivalent to one canonical. And it's invertible. Yeah.
Is this something like SON, n?
Not quite. No, but it's getting close to it, because if you recall, his point is, if you recall what happens in the case of rotations, you know that a rotation matrix satisfies R transpose equal to the identity matrix. Okay. It's orthogonal. If you look at 3+1 dimensions and look at special relativity and look at the group of boosts use as well as rotations, then those matrices lambda, 4 by 4 matrices, lambda transpose G, lambda equal to G, and you say it's pseudo-orthogonal. So in that sense, this guy is also pseudo-orthogonal. All symplectic matrices satisfy this. So you can see it's very close to that. So yes, I mean, I'm going to use this relation in order to find the Lie algebra. Yeah. No, I haven't said anything about the Hamiltonian. It's not. I've not even said that it's integrable. Yes. No, the new Hamiltonian need not have any such property. It need not even be functionally the same at all. Take the simple harmonic oscillator. If I make a canonical transformation to action angle variables, the action variable is essentially p squared plus q squared. So the new Hamiltonian is, apart from a factor of omega, just I. Linear in the action variable. Original one was quadratic. And the level surfaces were circles. Now the level surface is straight lines. So functional form doesn't have to be preserved. Is the change from, I look at a particle in 3 dimensions moving in space in a central force. Is the change from Cartesian coordinates to spherical polar coordinates a canonical transformation? If I just change x, y, z to r theta phi, the measure is not preserved. There's all the sine squared theta, d theta and stuff like that. So I also have to change the p's to pr, p theta and p phi, and that's a canonical transformation. You have to preserve phase space volume effects, not in configuration space alone.
Is it possible to preserve the symmetries as
No,
well?
not needed. Not needed. In fact, I try to do the opposite. I try to go to change of variables where the symmetry becomes manifest, as opposed to a very hidden symmetry. That's what happens in the Runge lens vector, right? In terms of action variables, it's a very simple looking Hamiltonian. But in terms of this original variables, p's and r's, it's a very messy Hamiltonian. There's p squared and then 1 over r. The level surface is some potato-shaped object in 6-dimensional space. But I want to express it in some very simple form. So the whole idea is to try to actually extricate that, extract that symmetry by a clever change of variables. So the whole study of canonical transformations can be reduced to the study of symplectic matrices, because that's what the Jacobian matrix is.
So this is determinant of Jacobian should be plus or minus 1.
Yeah, it says the determinant should be plus minus 1. You need, incidentally, this implies that determinant m equal to plus or minus 1. It implies that. But a little harder work will show you, and this is non-trivial, that it is in fact equal to plus 1, not this. So symplectic matrices have determinant plus 1. Good point.
So your first condition implies the second one.
Yeah, I mean, from this equation, if I just take determinants on both sides and use the fact that determinant AB is determinant A times determinant B, all I end up with is a statement that determinant M is plus or minus 1. But you need to do a little harder work to show that it's exactly plus 1. And that's a canonical transformation in our definition. So that will be the next step. I'm going to extract the generator of the Lie algebra of the generators exactly as I do in the rotation proof. And we'll see what those things look like.
There is one announcement. There was some request to get Chandan to give one more lecture. So tomorrow, instead of the tutorial at 4:30, Chandan will give one more lecture. So tomorrow, Thursday, 4:30 to 6, Chandan will give one more lecture on RG. And again, there are some feedback forms that we'll keep here. So it's here. You can, those of you who have not collected yesterday can take them and return it before the end of this. There are some more notebooks out here if you need to.